Welcome back. We're continuing our work in hypothesis testing, and we're going to be looking at testing a claim about a proportion. So we're going to use a sample of a population to test a specific claim. The requirements for this kind of testing is that we must have a simple random sample. So from the population, we must have a simple random sample, and the population must be a binomial distribution, and it must satisfy the requirements for a binomial distribution. And the size of the sample times the probability of a success must be greater than 5, and the size of the sample times the probability of failure must be greater than equal to 5. So now our notation, and I need to put a p hat here, and our notation is that n is our sample size, p hat is our sample proportion, and we've seen this in previous lessons, p is the population proportion, and q is, well, it is 1 minus the population proportion. So q is the proportion of failures in the population, p is the proportion of successes, and p hat is the proportion of successes in the sample. And when these requirements are satisfied, the binomial distribution of a sample proportion can be approximated by a normal distribution, where we say that the, let me grab my pencil here, that the mean is equal to the sample size, n, times the population proportion, and the standard deviation is equal to the square root of the sample size times the proportion of the sample p and 1 minus p, which is q. We're also going to need to find our test statistic, and that is a z-score, and that is p hat, which is the sample proportion, minus p, which is the population proportion, divided by the standard deviation, which is the square root of p, our sample proportion, times q, which is 1 minus the sample proportion, divided by n, which is the sample size. Now let's work an example. Okay, here we have an example, and it says, let's read it. In a recent poll of 755 randomly selected adults, 565 adults said that it is morally wrong to not report all income tax returns. Use the 5% significance level to test the claim that 70% of adults say that it is morally wrong to not report all income tax returns. We are going to do the following. Identify the null hypothesis, the alternative hypothesis, the test statistic, the p-value, the conclusion about the null hypothesis, and a final conclusion that addresses the original claim. So let's start by looking at the given. The first given is that we've randomly selected 755 adults, so n is 755. And that of the 755 adults, 565 said that it is morally wrong. So our x value, the count of people that say it's morally wrong, is 565. We are also given a 5% significant level. So our alpha, which is our significant level, is 0.05. And then the claim says that 75% of adults say it's morally wrong. So that means our claim is that the population proportion is equal to 0.7 or 0.70, that's 70%. And there we have it. This is our given. So the first thing we want to do here is identify our null hypothesis. Well, here we're given our claim about the proportion, that the population proportion equals 70%. And remember, our null hypothesis is one where our proportion is equal to a value. So this does represent the null hypothesis. So let's write that down. Our null hypothesis, get my pen, okay, H naught is that the population proportion equals 0.7. Therefore, our alternative hypothesis, which is H1 or HA, I like to write HA, is the opposite. If P is not equal, if P is equal to 0.7 is the null hypothesis, the opposite of that would be P is not equal to 0.70, 70%. So this is the answer to the first inquiry here, is that we are to identify the null hypothesis, which we did right there. And then the second inquiry is to identify the alternative hypothesis, which is what would be left, what other possibility could there be, and that's right there. The next thing we want to do is find the test statistic. Well, the test statistic is a z-score, and that is equal to p hat, which is our sample proportion, minus p, which is our population proportion as declared in our claim, divided by the square root of p from our claim times q, 1 minus p, divided by n. So let's go find these input values. I'm going to put them in black. So let's find p hat. P hat is equal to x over n. Okay, the number of people who said that it was morally wrong over the total number of adults. So x is 565 and n is 755. And when I put that into my calculator, I get 0.74, and it actually keeps going. I'm going to go to 3 significant digits. My z-score will be 2 significant digits, but this is being fed into the calculation, so I don't want to round this yet. So let's hold it at 3 significant digits and round the z to 2 significant digits in the end. Okay, so so far I have my p hat value, that's 0.748. Minus, well, the next value is p, which is the population proportion, and my claim says it's 0.7, so I'm going to go ahead and put 0.7 in there. And that's going to be divided by the square root of p, which is again 0.7. Now I had to find q. Remember that q is from the population, and it's 1 minus the p-value from the population. Well, 1 minus, oops, that should be a minus. Let's erase that dot there. Okay. 1 minus 0.7 is, I'm going to write it right above, 0.3. So let's go ahead and put q in. Q is 0.3. And it's really 0.30 and 0.70, but that's okay because there's no value with the 0. And we're going to divide that by n, and we know that n is 755. So divide that by 755. Now when I put this into the calculator, this I'm going to round to two places, and I get 2.88. And that is my test statistics. That actually represents the z-score for my sample. Now we're going to look at our p-value. We need to determine the p-value. And the p-value is the probability of getting a test statistic as least as extreme as the value representing the sample data. Well, in this particular case, we have to look at our significance level, and our significance level is 0.05. So to understand this, we have to think about whether this is a one-tailed test, a two-tailed test, or a three-tailed test. Well, when we look at our hypothesis, when our null hypothesis is equal and our alternative hypothesis is not equal, that's the clue. Not equal means it's a two-tailed test. Let's draw a picture of our probability distribution. I'm going to draw a little one here, just a small one. This is our normal distribution right here. Bell-shaped curve. Here's the center. I want to straighten out that center, I think. No, I guess I'll leave it. Okay, that's the center, which is where the x-axis actually represents our proportion, and that's a center where we would declare, well, the proportion is 0.7. Okay, and it has a z-score of 0. Now, because we are doing with the alternative hypothesis is not equal to, this becomes a two-tailed test. So we actually have two tails. We have a right tail and our left tail. And when you think about it, it's a 95% confidence interval. So 95% of our data is going to fall between the two tails. So since 95% of the data falls between two tails, then the tails, we have a tail here, and we have a tail here, then these tails are going to make up the remaining 5%. So the area in this tail and the area in this tail is going to be our significance level divided by 2. So it's alpha over 2. Well, of course, alpha over 2 is half of 0.05, so it's 0.025. That's the area that we're looking at here. Okay, now what we're going to do is we want to find the p-value. And when you think of the p-value, what I want to do is let me imagine, let me use blue. Well, I'll use red. That our test statistic z-score puts us right here, 2.88. And now I'm not really sure where it's going to put us, whether it's going to put us to the left of my alpha over 2 bar, or to the right of it. It could end up over here. I'm not really sure. But let's imagine it falls to the left, okay? So with it, if it falls to the left, then we know that it falls in the area under the curve where we would expect the population to be equal to 0.7. So it's like very close enough to be equal to 0.7 or 70%. If it falls to the right, outside of this 95% range where we're in a tail, then, or if it falls far to the left of this bar here, then we're going to reject our null hypothesis. So what I want to do is I want to find the tails that would be created by the two tails that we created by our current statistic, our test statistic. So I'm going to put another bar here because that would be the left-hand test statistics at negative 2.88. We're doing a two-tailed test. Okay. So what I want to do is I want to find the area in the tails here created by our test statistics. I'm going to have a different set of tails. And we want to know, is that tail greater or smaller? So our actual p-value would be the sum of the tails, the right and left tail that are now red. And to do this, we're going to use a function. Use our calculator. It's really the easiest. Is the normal CDF function. So to get that, we press second var. So we're going to press the second button on our calculator, and then we press the var button. And we're going to select number 2, and that's going to bring us down to the function that is normal CDF. Now remember, with the normal CDF, you give it the input. There are 2 inputs, there are 2 z-scores, and it gives you the area between them. So what I'm going to do is I'm going to get the area from a negative 2.88. Now actually I'm not looking for what's between negative 2.8 and 2.88, but the tails. So this is actually going to give me what is between them. Okay, I'm actually looking for the tails, not the area that's between negative 2.88 and 2.88. However, the entire area under the curve is 100%, or 1. So if I say 1 minus the normal CDF from negative 2.88 to positive 2.88, I will get 100% minus this area, which is going to give me the sum of my 2 red tails, and that is the tails created by my test statistic. Okay, so when I put that into my calculator and I round that to 2 significant digits, I get a p-value of 0.0040, and I can round that to 4 significant digits. Now our next step is to come up with a conclusion about the null hypothesis. So this is really based on our p-value. So this is our, let's write this over here. I'm going to use blue. Our p-value, which we just calculated, is equal to 0.0040. And when we compare that to the probability value for our alpha, or our significance level, 0.05, okay, that is the area to the right and to the left for our significance level. We're going to compare that to 0.05. We find that our significance level is actually greater than our p-value. If the p-value is less than or equal to the level of significance in a 2-tailed test, we reject the null hypothesis and conclude that there is sufficient evidence to warrant rejection of the claim. So since this is a case, we do reject the null hypothesis because the p-value is less than 0.004. In fact, I have this drawn incorrectly now that I've done my calculation. I'm going to see if I can erase this. I'm not sure. Okay, it's not letting me erase it. So in actuality, the bar for the 2.8 is on the inside here, and the bar for the negative 2.8 is inside these tails. Let's move that over. So, and I'll do a little arrow from negative 2.8. That's right there. It's inside the alpha, and positive 2.8 is here. It's inside the alpha. And so that means that we reject the null hypothesis. Okay, so let me write that down because that's one of the questions, that we are going to reject the null hypothesis. And since we reject the null hypothesis, we fail to reject the alternative hypothesis, H sub A, which is what we're supporting here, that the population proportion is not equal to 70%. So we failed to reject the alternative hypothesis, and so our final conclusion, that was the last, what a final conclusion that addresses the original claim. Our final conclusion is that the claim is not supported. The claim that 70% of adults say that it is morally wrong to not report all income tax returns, well, that claim, because we're supporting the alternative hypothesis, that claim is not supported. So I would say that the claim of 70% is not supported. There.